Hey guys, sorry that I was unable to deliver a lecture on Tuesday morning. For some weird reason, I got fever and I felt not great. And on Tuesday, I mentioned to some of you that I'm gonna do the recording for the lecture on Wednesday, but yesterday too wasn't my best day, so that's why the lecture is coming now. So and today is Thursday. So sorry about the delay. All right, so I'm not planning to spend too much of the time for today's lecture, but basically going over the material that I wanted to introduce to you, and the material that I wanted to introduce you today is stress and fatigue prediction. This is one big subject matter. Another one is summary and how to prepare yourself the next midterm exam. And as I have understood, so now the voting action for what kind of questions will be, what question will be there in the midterm exam is already undergoing, and what question will not be there is also undergoing. So please enter your answers, please cast your vote, and the results will be available a little later. Okay, but without further ado, stress analysis based on multi-body system dynamics. Shortly about this subject matter, and this, of course, is something that comes with a great practical relevance. And the great practical relevance because stresses are typically the quantities that design engineers are very much interested in. So what we do in the multi-body system dynamics is that we do know the forces, and if in the case of deformable bodies, we do know the way they deform. But the one thing that we do not know yet, but we will right after this lecture, is what about the strains and stresses? You do know that displacement, the way the structure is deforming, is related to strains, which in turn is related to stresses. And how you can move forward from this deformation, from this displacement, the way the structure is deforming, all the way to stresses, that's what this lecture, or the first part of the lecture, is about. We have basically two ways to make things to happen, and both are okay. One is my preference, another one is something that is kind of straightforward that comes with a little bit of practical difficulties. And these two ways are as follows. So what you can do once you have analyzed your multi-body system dynamics is that you can use all the loads, which is all the forces, including joint forces, which are reaction forces, and inertial forces, and maybe the context, whatever forces you have imposed to the body, you go and take and export them from multi-body system simulation software to finite element software. And if doing so, you of course have a great benefit that comes with the fact that finite element software has a fantastic post-processing opportunities, and all of that is in your usage if you do so. This is a little bit of clumsy way to get strains and stresses because if you think this carefully, so what you do then is that you actually have a deformation in your flexible multi-body system simulation, but you're not making use of that information, but instead you take the forces and export them to the finite element software. And another, or let's say, alternative for this is to make a use really of those displacement directly in a multi-body system dynamics. So take the information you need to get from the displacement, the deformations, all the way to strains and stresses. And this is the second opportunity, which is the usage of uses based on the model stress matrix. So this model stress matrix is basically the package that tells you how the nodal displacements are related to strains, and then how the strains are related to stresses, which is typically just a matter of model elastic modulus, how that can be conducted. This is super efficient, straightforward to use, but problem is that's not necessarily available in all the software, multi-body software that you might need to use in the future. Okay, so here's a little bit of graphical representation, how it's gonna go. So it's gonna go like this. So you take all the forces, including the angular velocities, acceleration, which is inertial forces, related to inertial forces, and you export them to finite element software. And then uh, you introducing the boundary conditions some kind, because you must do that, otherwise the system is not going to be able to make any kind of predictions about the strains or stresses or deformations at all. And then you conduct multiple static analysis to get what? To get displacement. And then displacement, which is a primary unknown in a finite element software, you can get the strains and stresses by using all these tools that is available in finite element software. So basically, you could use the same software that you extracting the modes. Same finite element model, you extracting the modes, you exporting that to multi-body system dynamics. You run your models. Sorry that I'm blocking a view a little bit. You run your analysis, and then once you're done with your analysis, you take all the forces, you put them back in a finite element model, and then you recompute the deformation. And then, because you have a use of all these nice post-processing tools in a finite element software, you can get the strains and stresses. That's it. Okay, alternative. Let's look at the details of the alternative. So it works like this. In a flexible multibody dynamics, when using the floating frame reference formulation, you are solving the modal coordinates. And modal coordinates are related to nodal displacements. And they are related to nodal displacement via this deformation matrix. The matrix that tells you how are the assumed deformation modes. This one that you can get from Craig-Thompson method, or just an eigenvalue analysis. It doesn't really matter how you do it. But anyways, you have an access to this information. And once you have the modal coordinates solved from the equation of motion, you can go back to the nodal displacement. Okay, nodal displacement, this is clear. This is nothing new. But we need more. We need more. Remember when we discussed about finite element modeling, we discussed that nodal displacement and strains are related via kinematic matrix. Kinematic matrix is a relation. So now if you have an access to kinematic matrix, all you need to do is multiply this displacement by kinematic matrix, and you can get the strains. Okay, here it goes. So you first compute, let me get started from the beginning. So this is a p dot dot, and once you're solving the equation of motion, you can get p. Now, once you get the p, let me move this up. Okay, I think it is clear enough. Once you get the p, you can get the nodal displacement. And then you need to break these to element level, so you need to look at for each of the elements, how is the deformation within the elements. Then you get this kinematic matrix. This is something we discussed when we discussed about finite element method. You can get the strain. And then with the help of the matrix of elastic coefficients, you can get the stresses. And that's it. Now, if combining all this information, you can multiply this matrix of elastic coefficients, kinematic matrix, and modal matrix, and all that. This combination of three matrices is called modal stress matrix. And that's an alternative. This is very modern. This is a super nice way to go. Problem is that it's not necessarily available in all the software applications. So here's a summary. All right. So you take the forces, send them back to finite element modeling, finite element software. You conduct multiple static analysis to get the deformation corresponding each of the time step you did in your multi-body software, and then you can get strains and stresses. This is how you can possibly build stress histories. Or you can use a model stress matrix where you make use of the information about kinematic matrix, modal matrix, and matrix of elastic coefficients. And once you do that, then you can plot the stresses directly in multi-body software. Okay, what to do with that? Okay, why this is important? Of course, you can use the stress information to make a design in the better structures. You can optimize stuff. That's one thing you can do. But one thing that is very much in practical usage is use the information for fatigue analysis. The fatigue, particularly when looking at the fatigue of welded structures, is very relevant because most of the heavy machinery are made by welding steel parts together. Now, the welding is very affordable, very economical way to combine things and is technically very solid too. But it comes with a problem, and the problem is fatigue. Fatigue is something that is hard to avoid. There are tools that you can alleviate the problem, but it's hard to get this, get completely rid of this problem. This is just very, very complicated. Actually, this is something that, when look what's happening in the future, fatigue analysis is probably more important in future than it is today. Reason is that there's a big desire to make heavy machinery to be lighter. And the easiest way to make that to happen is to change the material from conventional steel to high strength steel. And when you do so, the fatigue is even bigger problem than it is at today. We'll explain this momentarily, like why is this? Why is this case? All right. So, some reason this, I guess that I need to tune a little bit about my, like this. Oh yeah, I see that. Okay, let me do like this. Hmm. Was it like this? All right, so much better now. Sorry that it wasn't perfect in the beginning of the lecture, but now it's much better. All right. So you can do the fatigue prediction if you know the three things. You need to know the material, which in a steel material is just steel. That's what you need to know. Then you need to know the geometry. So you need to know a little bit about the details of the joint you're dealing with, the joints that you're predicting the fatigue. And then the most cumbersome, the most difficult part, you also need to know the loading history. Loading history, not easy to get. That's gonna be hard for sure, because to make this correctly, the accuracy of the entire procedure depends on three things. But I'm saying that material is not too complicated to get that part of the equation, as is the geometry too. But the loading is very, very difficult. And it's important to keep in mind that the fatigue is a statistical thing. So you cannot say that for sure every single machine is going to break with this and this amount of hours, but you can say what percentage is probably damaged after this and that number of hours. So probability is a big deal of the the fatigue life prediction. And this is good to keep in mind. And typically the prediction and the fatigue life probability, what we wanted to get is that the undamaged percentage is 97% or something like that. That's typically the thing. And now if you want to learn the details, I really recommend you to participate the course that is, I think that it is entitled as a fatigue prediction or something. This is my 10, 15 minutes max highlights, cannot cover all the details. Okay, fatigue life or damage, how is evolving, consists of three things: crack initialization, crack propagation when the crack is growing in a structure, and then what happens in a fraction of the second is a final fraction when things are separated. So those are the three phases. Now, I said earlier that welded structures are not great in terms of fatigue, and it's simply because of the initial crack is typically already in a structure when you're dealing with a brand new machinery or structures. And this is because of the welding process introducing initial defects, which are imperfection at the welded joint. And welded joint is this particular region, like this one here, the black I mean, the area that is color coded by black color here, that representing the weld. This is a one steel plate, and here's another steel plate, and this is where they're connected. Now, the welded toy, this particular detail, when you take a close look, what happened here, you can see that there are initial cracks. And that's simply because of the welding process. So the welding process makes that to happen. And that's a big problem because in a machine components like crankshaft, the components that you can find in your car engines, they fatigue life mainly consist of initial crack propagation. I mean, how the initial crack grows. Whereas in a welded structures is already there, and it's hard to get rid of that. There are post-processing technique that helps, and they're like you can go and heat this welded toy by TIG welding. You can use a hammering to get rid of this, but it's all of them are cumbersome to use, not easy to use. Crack propagation, that's when the crack is growing. That takes the most of the lifetime. Like I said, the final fracture takes a fraction of the second. All right, we're not gonna have in-class quizzes here because you know this is recording, not online. Geometry. You know what happens because of the geometry is that when you take a close look about the stresses, very near where the crack is growing here at the welded toy, because of the geometry, the stress started to increase quite a bit. And this is because of this non-linearities in a structure. And this causes the stress to go quite high. Another not great thing, because this is another reason that the fatigue in a welded structure is a quite serious problem. Okay, when we do the prediction of stresses using multi-body system dynamics, we cannot take these very accurate stresses that are applying exactly in the location where the crack is growing. This is not going to be possible. This is no way. I mean, that the computational accuracy is not good enough to take this kind of level of details into account. Not possible. Okay. In my introduction to fatigue, I mentioned that the fatigue is a big problem, but it becomes to be a bigger problem in the future because we want to make more use about high strength steel. Now we learned earlier that welding is a problematic because the welding introduces initial cracks at the welded toy. All right, but that's not all. There's even more bad news, and the really significant bad news is that because the welding process, the welding goes such that you introducing excessive amount of heat here where the weld is located at, and then you allow that to cool down. And because of this welding process, what happens when you look at carefully, locally, now I keep this in mind that this is very, very local thing that I'm explaining here. Locally, when you look at the area where the crack is propagating, when the initial crack is located, there are high residual stresses. Residual stress is because of the amount of heat introduced during the welding process. Okay, what that means? It means this. Here's this famous curve where you have a strain and stresses. This is how the steel material behaves. So you have this linear curve that ends at the point where the plastic zone started. Now, because of the welding process, the residual stresses most typically goes all the way up to the point where linear region ends and plastic region starts. That's bad because now any kind of extra strain, any kind of extra loading will make the structure to deform plastically. I mean, now keep in mind, very, very locally. There's going to be local plastic deformation, and this local plastic deformation is exactly where the crack is growing. And this is a mechanism that makes the welded structures to be very vulnerable for fatigue damage. Okay, now you say, yeah, all right, so let's change the material to be high strength steel. So what's the difference between conventional and high strength steel is simply that this linear region is going to be longer in high strength steel. So let's do it. Let's change it. So what's the difference? No difference. because again, heating amount of heating we're introducing in the welding process is so significant that regardless how long is your linear region, you always end up to be in a point where the linear region turns out to be plastic region. So that's much about the help of the high strength steel. Now the big problem is this: because of the high strength steel, you have this ability to make structures to be more slender. And now when you do so, the loading will be higher than it would be in a case of conventional steel. That's it. Okay, now let's just think that, okay, we are capable to get the stress history using the technique that I just explained in the first part of my lecture, so you can get it. And the stress history, once is in your use, what you should do with that? Well, what you should do with that is this: you should calculate, the stress ranges, deltas of stresses, because what matters in a fatigue is not so much about, what matters a little bit like how, where is the level of stresses where they're traveling. But most importantly, if you take stresses on and off, this is something that is very, very dangerous in terms of fatigue. And what you do in the first part of the fatigue-like prediction is that you need to recognize what are the deltas. How much are the ranges of stresses that are fluctuating in your particular detail. Probably there's a many different kind of deltas. There's the small ones and big ones. And what you need to do is that you need to put them all, you need to combine them all, you need to calculate something that is called equivalent stress loading, which means that you replace the time, or this is like a reference unit. It could be like one work cycle, it could be 1 hour. You replace that by one single delta that is equally dangerous than these small ones and big ones all together. And now, once you get this information, this is finally the one that you are ready to go for fatigue analysis. And then you have multiple choices. You can use very simple approaches. You can use this level of stresses you can easily get by using multi-body simulation, which is these nominal stresses. And you can compare the stress, this big delta, to pre-calculated tables and make an estimation about what's the fatigue life. And this is a method based on nominal stresses. Or you can go more detailed. You can use a hotspot method, which is no longer that much in a fashion. Right now, the one that is more in a fashion is called 4R method. The one you can learn more from if you participate in this fatigue course. Anyways, so you can get more detailed information into account. You can get more accurate stresses, exactly where the crack is growing. And you can get this more information from literature, from detailed finite element or boundary element analysis, or even from the measurements. And then you can use more advanced method that is called hotspot method. You can even use a fraction mechanics. In the fraction mechanics, you can use it. You need to get more accurate stresses, which you can get from literature, or again using more detailed finite element or boundary element method. All right, so this is what I did more than 25 years ago. So when I do the math, this was 28 years ago when I was finalizing my doctoral dissertation. So this is a crane that we still use in the lab. So this is a crane that is a lock crane. And the idea of the lock crane is to move lock from the ground to the trailer. That's it. And what we did was we modeled these using flexible multi-body dynamics with hydraulics, with contacts, with everything. And once we were able to do that, then we were able to verify how it behaves in terms of pressures. And this picture is blurred, but if you look at carefully, this is me sitting in the back of the crane here, and this is a verification comparison between the simulation and measurements, and they were in a good agreement. And then we were able to use the stress history computing. This is how the stress history looked like. So we attached few strain gauges in a point A and B, and we measured and simulated the stress histories, and this is how they are in an agreement. All right, so finally, once having this information, we were able to make a fatigue life prediction. And this particular design wasn't very great design. Here's the reason. Because there is a hydraulic pipes that goes to this telescope cylinder here, and these pipes were connected to upper part of this boom here by using the small welded nuts here. Whatever you use of welding, you need to understand that it comes with a risk. So what you really wanted to do is that you want to take a welding as far as possible from the highly stressed area. And when you look at carefully, this area happened to be the most stressed. This is where you can see that obviously the highest stress is definitely located here. And accidentally, this is exactly where these welded nuts are located too. And they don't need to be there because you can put them anywhere else you want. And, and this is a good lesson you to learn. So whatever you use a welding, look where the welding is located at and put that away from the highly stressed areas. Okay, another in-class quiz which we're gonna simply skip. All right, we reached the summary. So these are the things. So we can ask questions about bicycle dynamics, model reduction, contact modeling, stress analysis in multi-body system dynamics, and fatigue analysis. These are the 5 subject matters. And now you have the questions. Well, let me just show the questions that are in the model reduction. How does the model reduction reduce the computational effort? 2 ways. First of all, you can reduce the number of unknowns. Another great benefit is that if you get this model reduction using orthogonal modes, then the coupling between the unknowns, which are the model coordinates, will disappear. And then you can solve the system by as using 1 degrees of freedom systems. What are the key steps applying the Craig-Bampton method? Craig-Bampton method works like this. So you are taking your finite element model, like the plate structure here. You are dividing your nodes to boundary degrees of freedom and interior degrees of freedom. And based on this selection, you reorganize your mass and stiffness matrices, and you conduct the 2 different kinds of modes. The one that is associated to interior degrees of freedom, the one that is associated to boundary degrees of freedom. That the boundary degrees of freedom, you introduce in the unit displacement, and then you see how the structure is behaving. Okay, you can get 2 set of modes, which is called fixed interface modes. This is the one that is based on this interior degrees of freedom only, and the static modes that are based on these boundary degrees of freedom. Now, boundary degrees of freedom, or more accurately, static modes, are not orthogonal. So what you can do then is that you can force them to be orthogonal by using something that is called orthonormalization. And once you do that, then you can get the modes that are roughly free modes and roughly boundary modes. And then you're good to go. That's it. Model reduction, so we discussed this already. Contact modeling, explain the concept of bounding boxes. This is the contact prediction procedure and how contact can be modeled using penalty forces, which is based on the penetration indentation. What are the advantages and disadvantages associated to penalty force approach? It's straightforward to use, but it's sensitive for integration settings, in short. All right, so bounding boxes comes with a different size of boxes, and then you check if these big boxes in the root level are colliding, if they are penetrating. If so, then you're moving the more detailed boxes and look if they are penetrating. And again, if so, then you're gonna move on to the final level, which is the leaf level. And these are the drawing primitives. And then you can see if there's any chance that they are penetrating, and if that's the case, then you push these 2 parts away from each other by using penalty forces. Okay, so we learned that there are 2 different ways to describe the penalty force. I mean, the contact itself, penalty force is a complementary approach. And what I wanted to say about this one here How contact can be modeled using penalty forces. So it's basically based on the how much these rigid bodies are penetrating, how much they are sharing the same geometry. And based on this information, you push them away from each other, and that's how it works. Advantages is that it's straightforward to use. It cannot work well if the mass differences of the bodies are great. This is hard to make it use well, and it's quite sensitive for integration settings because if the penetration becomes to be unnaturally high, the forces will be unnaturally high. I don't know why somehow this is a little bit of mess about my presentation here. The next one here is stress histories, how the stress histories can be evaluated using the multi-body system dynamics. That what we just described, two methods, exporting the loads or using the model stress analysis matrix, and finally fatigue analysis, why the welded structures are so weak in terms of fatigue damage. First, because of the welding process introduced the initial cracks. Secondly, because the welding process introduced the high residual stresses. All right, that's it. Gonna close this recording, paste it in the YouTube. Too bad that we were unable to see in the last lecture. I really miss that. But what are you gonna do? Sometimes the life is like what it is. All right, you guys take care and see you next time.